Okay, we just proved that this 1 over 2 pi I times the integral along gamma. Gamma is closed rectifiable curve. dz over z minus a is an integer. Okay, so we just showed it is an integer. This integer has many interesting properties. So because of that, we gave it a name. Let's see, 4.2 definition. If gamma is a closed rectifiable curve in C, then for A not on gamma, this number, you see the number is an integer of gamma with respect to A, okay? We define it to be 1 over 2 pi integral along gamma dz over z minus a. dz over z minus a, okay? And this number is called the index of gamma with respect to the point A. Okay, so because of this construction or the computation, we know it definitely depends on gamma. Also, it depends on A. So it should be function of a gamma and A. So that's why we say with respect to A. And it is also called, it has several names because it has different applications or usage. It is also called the winding number of gamma. Around A, the winding number of gamma around A. So this is a winding number. You possibly see this name more often than the index, because index, this word, has a lot of different meaning. For in different subject, you may have this index, you may have that index, but winding number is especially for this definition. Okay, this is the winding number of gamma around A. All right, so now let's see some algebra about the winding number. So let's recall. So if gamma is from 0, 1 to C is a curve, then we can define negative gamma or gamma to -1. It depends on how you define the operation. If you use addition, this is negative gamma. If you use multiplication, this is gamma -1. Is the curve defined by negative gamma of t is equal to gamma of 1 minus t. Okay? So basically, if your gamma is this direction, counterclockwise direction, this is gamma, then go clockwise, this will be the negative gamma. The same trace, only different rotation, different orientation, not rotation, different orientation. Okay, then this is a negative gamma, or gamma inverse. And if gamma, sigma are curves defined on this 0, 1 with gamma 1 is equal to sigma 0. Okay, gamma 1 is equal to sigma 0. So basically you have a gamma this way. This is gamma 0, gamma 1, and the gamma 1 is an initial point of sigma 0 and sigma 1. This is like you join them together. All right, then we define gamma plus sigma. Gamma plus sigma is from gamma 0 to sigma 1. And first half you apply gamma, second half you apply sigma. Right? We define gamma plus sigma is a curve or the curve such that the gamma plus sigma of t, it is gamma of 2t if t is between 0 and 1/2. And it is a sigma of 2t minus 1 if t is greater than or equal to 1/2 and less than or equal to 1. Yeah, in the textbook, that's not, this one is the right one. It's a 2t minus 1. It's not 1 minus 2t, right? We need the sigma to have the domain 0, 0, 1. Yeah, this is the right one. 2t minus 1. Okay, so with this inverse and addition operation, we have the following simple proposition. First of all, this addition, negative element and addition works for all the curves, not necessarily closed curve. Here I use closed curve, but it's not limited to closed curve. Arbitrary curve will be okay. Okay. But if we want to apply this construction to the winding number, we need gamma and sigma to be closed curve. If gamma and sigma are closed rectifiable curves, closed rectifiable curves having the same initial point. The same initial point. Then we have the following one. For A not inside gamma, the winding number of negative gamma with respect to A is equal to negative winding number of gamma with respect to A. So here you change the orientation, you get a negative sign. Okay, and second, for A not equal to gamma union sigma, and the winding number of gamma plus sigma with respect to A is equal to the winding number of gamma around A plus the winding number of sigma around A. It has additivity, and the negative element will give you a negative winding number. Negative of the winding number. All right, so you can try to prove this. This is not difficult. You just change a variable. Change of variable process. Okay, so that's all. The proposition 4.3. Remember at the beginning, before we prove this this winding number theorem, I mentioned that if you have a circle, remember this gamma t is a plus re 2 pi I t, yeah, 2 and times n, 2 n pi I t. Here t belongs to 0, 1. and we computed integral along gamma dz over z minus 1. If you don't remember, just go check it. This is exactly equal to n. And then this n is the winding number of gamma with respect to a. Okay? So this is an integer n. This integer can be positive, can be negative. Can be positive, can be negative. What does it mean? So even though this t is from 0 to 1, but once you multiply this 2 pi I t by n, actually this is a. You wrap this circle n times. Okay, when t changes from 0 to 1, you actually turn around n times. Okay, so this is the reason. The winding number actually tells us how many times your curve surround the point. N is the times of the circle wrapping around A. So that's why it's called the winding number. Winding number. Okay? And in the book, they gave another imprecise argument about this winding number. Okay, so assume that gamma of t is smooth. Gamma of t is smooth. This this integral, the winding number becomes this. This is still the winding number of gamma with respect to a. And we recall that the derivative of the natural log of f of x is f prime of x over f, right? The natural log of f of x has derivative f prime over f. So this is actually f prime over f. If logarithmic function makes sense, well defined, we will have this integral equal to 2 pi I the logarithmic function of gamma of t minus a from 0 to 1. Okay, so what is t equal to 0? So for example, we have a. T equal to 0. This is a gamma of 0. And gamma of 0 will turn around. Here I only draw 3 times and back here. And the argument, this is alpha. Okay, so you will have, if you follow this, you will have 1 over 2 pi I gamma natural log absolute value of gamma of 1 minus a and plus I the argument, right? The argument after you surround. So this is the initial one. When you move back to here, you will get actually the identical part, but you will have I plus the argument. What is the argument? It's alpha plus how many times? N times 2 pi. This is here I draw 3 times. Here n is equal to 3. But in general, n can be anything, right? It depends on how you surround it. This is the value when t is equal to 1. And subtract natural log of value of gamma of 0 minus a I alpha. Okay? And gamma is closed curve, so this real part canceled. You only have imaginary part survives. Alpha canceled, so the initial argument is not important. The important thing is like the increment. You surround like n times, so it's n2 pi I over 2 pi I. This is n. So it's still the number of wrapping, the wrapping number. Of gamma around A. Of gamma around A. Okay? So this is definitely the wrapping number of gamma around A. So that's why, that is the reason we call it the winding number, the different word, but with the same name, All right? After we study this, we have a interesting observation, actually. So what is the observation? At the beginning, we mentioned this winding number. Depends on gamma and A. Okay, depends on gamma and A. But here, it's just about the number of times, wrapping times. So A is here, you get the wrapping time equal to 3. If A is here, you still get the wrapping time n equal to 3. But if you move it to the other region, then the situation will change. The answer may change. Okay? So what is the difference between this region and the other region? They are not connected. So we will naturally have a observation in a connected component. The winding number should be a constant. Should be a constant. So it means in this in one connected component of what? The region surrounded by gamma. It is actually the C without the gamma, without the trace. When you remove the boundary, you will have different regions. All right? So should be, that's our observation. So it means this in each connecting component, it only depends on gamma, not depend on A. Every A will give you the same quantity. That's the observation. And for this is a huge exterior part. For this huge exterior part, it does not wrap around the number. So if you pick up, if A is outside of gamma, then the winding number should be 0. Right? Should be 0. It does not wrap around the A. Okay? So that's our observation when we try to understand the name of the winding number. Okay, so we're going to prove what we observed is correct. Is correct. And before that, let's have another little topological observation. So gamma is a closed rectifiable curve. then the trace of gamma is compact. Compact bounded. In the Euclidean space, compact will be definitely bounded. Okay, it's compact. Compact, then there is R greater than 0 such that, so if, for example, you have a gamma, this is a gamma, and this is center, origin. Then you choose a huge disk to cover this, to cover the gamma. This is R. If it covers the gamma, then the outside exterior part will be totally contained in the exterior part of gamma. So what is the exterior part? Then what? The region Z, modulus of Z greater than R, the exterior, will be contained in the complex plane without gamma. Complex plane without gamma here, you can call it, in the textbook they call it a G. Okay, so this G, it's just a name, has a unique unbounded component. Because if that component, if it has an unbounded component, it must contain this one. It must contain this. This one is a neighborhood of infinity. This is a neighborhood of infinity. Exterior part of the closed disk is always a neighborhood of infinity. Okay, just one, because whenever you have unbounded component, it will cover totally contain it. Then that's unique. Okay, now let's see the next theorem which we just observed. So let gamma be a closed rectifiable curve in C, then the winding number of gamma with respect to A is constant for A belonging to a component of G. G is C without the trace of gamma. Okay. Okay, so that's our first one. It should be a constant over the connected component. Also, the winding number of gamma with respect to A should be 0 for A belonging to the unbounded component of G, unbounded component of G. So outside you should have 0 winding number because the curve does not wrap around it. All right, so we're going to prove this. Oh wow, how do we prove it? It's a winding number. Remember, winding number. So here gamma is fixed, so A changes. So we define a function by Fa is equal to the winding number of gamma with respect to A. So F is defined over G because G is a complement, the complement of gamma. Every A in G does not belong to gamma, so you can compute the winding number. Okay, it's just one. It takes an integer value. Even though we put C here, it's an integer value. Okay, so we will show that f is continuous. Why we need this to be continuous? Because f is continuous, it will map a connected component to a single point, because the image is a totally disconnected set. The image is totally disconnected set. So that's why when f is continuous, the preimage will be a connected component. Okay, you can imagine that if, for example, if you have a 1, two point connected from one point to another, 2 point in the same connected component, then this is connected. If they mapped to z not connected, that will be a contradiction, right? Yeah. Okay. Let's see f is continuous. How do we show f is continuous? F is continuous. This continuity is not uniform continuity, it's regular continuity. So choose, not choose, just select A in G. Okay, so A is in G. Then we can draw the largest interior disk, a largest disk centered at A with radius R, totally contained in the contained in G. Okay, so let A be the distance between R be the distance between A and the gamma. Why we choose gamma? Because gamma is a boundary. If you do not cross a boundary, you are still in the same connected component. Once you touch the boundary, you're outside. You're out. Then that is the largest possible radius. Okay, so this boundary, this is a part of the gamma. I'm not saying it's a whole gamma, it's a part of the gamma. All right, so this is R. A here, we're going to choose B very close to A. So we choose B. For B minus A less than delta less than 1/2 R. 1/2 R. Less than 1/2 R. Okay? Very close. In the internal circle. Okay. Now let's see the difference. We're talking about the continuity FB minus FA. A and B is close enough. We want to see if FA minus FB is small enough or not. So it's 1 over 2 pi, 1 in number, remember. Ops value, integral along gamma, 1 over z minus A minus 1 over z minus B dz. All right? This is constant number, positive constant number. You can move forward. I with the modulus is equal to 1. This is equal 1 over 2 pi, integral along gamma. You do the computation B minus A, Z minus A, Z minus B. All right. Okay, so let's check. You're going to put this ops value into the integral. You will have integral gamma A minus B, Z minus A, Z minus B, dz. Z is here. Z is on the gamma. The distance between Z and A, this distance, should be greater than or equal to R. All right? It should be because R is the shortest distance. This is R. Greater than R. And check here. it's bad. This total is r. The internal part is 1/2 r. So b is inside here. Then the distance between b and z, it will be greater than 1/2 b, 1/2 r. Right? 1/2 r is a minimum, smallest possible value. Okay, a minus b is just a minus b. We don't care it. We don't change it. A minus b will be delta. Okay, so let's check. A minus b will be less than delta. So it's less than or equal to 1 over 2 pi delta. A minus b less than delta. Integral along gamma. Z minus a is greater than r, so it's flip it is less than. This is a 1/2 r dz, right? And you move this forward, you will get what? You flip this to upward, you cancel pi, you get 1 over r squared pi delta, and you integral of upside of dz, that's the total variation of a gamma. All right, so if you want this correct, you will set it less than epsilon, so you choose delta equal to epsilon r squared pi over total variation gamma. Remember, we're talking about the continuity at point A. So this r is a fixed. Once you get A fixed, r depend on A. R fixed when A is fixed. So this proved that f is continuous at A. F is continuous at A. Then f will map connected component to connected set. Of Z. Connected sets of Z is just point. Okay, a point means function is a constant over the connected component. All right, so that's the part of the proof. We're not done. We only prove that in one connected component, it's a constant. Now we're going to show if it's outside, it will be 0. Okay, so let U be the unbounded connected component. Unbounded connected component. All right, so there is an r greater than 0 such that the ball, the exterior part of the ball is totally contained in U. We just mentioned this, right? Okay, we pick up A. Choose A with upside of A greater than R. Very far from the origin, far from the origin. Okay. Okay. And let's check. So curve is here, gamma, and you choose A very far. So you can require modulus Z minus A is greater than certain number. So far, I don't know. At this moment, I don't know greater than certain what number, but you can just choose A sufficiently far so that D minus A, the distance, will be greater than whatever number you like, right? Okay, this uniformly. Let's put m. Let's put m here. Uniformly on gamma. Uniformly on gamma. Okay, now let's prove the winding number gamma a 2 pi I integral along gamma dz z minus a. I'm going to show the winding number is 0. Show the winding number is 0 is equivalent to show the ops value of the winding number is 0. I put the ops value. Okay, when I put the ops value, the I disappear. And I'm going to pass this ops value into the integral. All right, and z minus a modulus is greater than m, so it's less than or equal to 2 pi m. 2 pi m, and integral dz. And this is okay. This is a total variation of gamma. Yeah, total variation. All right. So So we want what? We want to prove this one is less than epsilon for arbitrary epsilon. We want to prove this one is less than epsilon. If this is correct, then what we have? We have m should be greater than 1 over 2 pi epsilon times the total variation of gamma. We solve for m because what? Because here we just say we choose an a with this condition, with this condition. So this a can be very, very, very far from the gamma. How far? It is controlled by epsilon. If epsilon is very small, you just choose a very, very far away a. If epsilon is tiny, it's not small, you choose a smaller m. But remember that this we choose if we have this, then the winding number will be less than epsilon for arbitrary positive number. But here you will see that this selection of a depends on epsilon. You have epsilon, you choose a different m, you choose different m, you get a different a. But n gamma a is constant on this unbounded set, unbounded connected component. Constant, it doesn't matter which a you choose from this connected component, you will get the same quantity. The same quantity is less than epsilon for any epsilon, any positive epsilon. So this quantity must be 0, right? So even though in the writing it depends on a, but the first part of the proof already show that over this connecting component, the selection of a, the choice of a, is not that important. It's always a constant over this component. All right. So that is the proof to show over the unbounded connected component, the Wanting number is 0. Why can we do that? Because we can choose sufficiently large m. You can name how large it is by choosing this epsilon. So again, in the textbook, there is a minor error here. In the textbook on page 83, 1, 2, 3, 4, 5, 6, 7, line 7, z minus a ops value is greater than 2 pi negative 1 total variation of gamma. Here you should put epsilon. 2 pi epsilon to the power negative 1 times total variation. If you do not put epsilon, then that m does not depend on epsilon, then it's not correct. Okay? Be careful. On page 83, there is a minor mistake, minor error, typo. Okay, so we showed this, we verified the observation we had. It's important. Okay? So the Wanting number is stable in certain sense. We say it is stable. You shift this base point A a little bit, you do not change the Wanting number. Okay? So that is a very, very important property. The Wanting number is a very, very important property. It is an example of many other so-called index theory. It's an example of many other index theory. Wanting number is also called the index of this closed rectifiable curve with respect to the base point A. Right? Okay, so we finish this discussion, and we will continue in the next video. All right? Thank you very much.